All right, hey everyone, thanks for coming out. We have a great talk because today we have with us Professor Chris Lintott. He's a professor of astrophysics at the University of Oxford and is also known as the presenter of BBC's The Sky at Night. Today he's going to be talking to us about his new book, The Crowd and the Cosmos, which details his creation of the Zooniverse, which is a crowdsourcing platform that lets everyday science enthusiasts take part in cutting-edge research. The Zooniverse project lets anyone with a computer classify galaxies or keep tabs on endangered giraffes or investigate the history of Australian prisoners. So there's a lot of really cool stuff, and I recommend that you check it out, but probably after the talk. So now, if you don't mind, please make sure that your cell phones are silenced and join me in a warm welcome for Professor Chris Lintott.
Thank you. Thank you very much. I turned the microphone on, I hope. Yes, thank you for being here, taking time out of your busy days. I really want to start with the fact that we're in the middle of a revolution in astronomy. I grew up as a small kid with a telescope, more about which later, but I thought I'd missed out because for me the golden age of Apollo, of Neil Armstrong's one small step, of space exploration, crewed exploration, was over. But I've slowly come to realize that this is the golden age of astrophysics, of astronomy, of understanding the universe. And so when we look at a night sky, and this is a randomly selected picture of a random piece of the night sky, yes, we see the same stars we've always seen. You can see the bright nebulae, the gas there from which new stars will form. And if you know a little bit more, you know that some of those dark patches are places where there's dust, grains of carbon and silicon from which planets and indeed stars might go on to form. But now, for the first time in history, when we look at a star field like this, we now know that most of those stars have planets. And so we're looking not just at sort of the glorious universe, but we're looking at a map of the worlds that we can imagine exploring. And I think there's something really profound about that idea, that when you go outside and look up, if you spot a star in the night sky, it probably has planets going around it. I can even show you some of those planets. This is my favorite astronomical observation. This is a star called HR 8799. Astronomers should not be allowed to name anything, but HR 8799. Actually, most of the light from the star is missing here, so we've subtracted it away. The little yellow thing in the middle is not what the star actually looks like. That's been added back in. But if I animate this over the course of several years, you can see there are 4 blobs in orbit around the star, and those are 4 planets going around this star. They're called HR 8799b, C, D, and E, because astronomers shouldn't be allowed to name anything. They're a bit bigger than our solar system, so the innermost one goes around once every 45 years, the outermost one once every 460 years, and they're a few times bigger than Jupiter at the largest and Neptune at the smallest. So it's like an exploded version of our solar system. But really, my point is that we've all seen this animation. Every time Brian Cox goes on television and pontificates about planets, you see this for our own solar system. But this is real data, and we can now watch planets going around another star. Now, for most of the stars that we found have planets, we can't do that. Normally the glare of the star is too bright. It's not that the planets are too faint to be seen, it's that the stars are too bright. And picking out Earth-sized planet around a sun-like star, even in our local galactic neighborhood, is rather like trying to spot a firefly flying in front of a stadium floodlight from about 50 miles away. So what we do instead is come up with indirect ways to discover planets. This is an object that you will have remembered from the summer. This is the sun. We haven't seen it for a while. But this is the sun on a particular day in 2012 when Venus went in front of the sun. It's called a transit of Venus. Things like this, Venus transits the sun about twice a century. The next one's about 100 years away. But it's quite a spectacular sight. On the right, you've got the exciting version of this, never mind the video. This is a graph made with a school light meter, which records the total brightness of the sun. And you can see that when Venus is in front of the sun, it appears slightly fainter. Astronomy is a really simple science. We deduce that something must be getting in the way of the sun. And if you were in the right place in the galaxy, such that this alignment happened every time Venus orbited the Sun, you'd see a repeated pattern of dips. And from that, you could deduce that there was a planet there. You have its orbital period, and you might even work out the size of the planet based on the structure of this dip. So that's what we do. We look at hundreds of thousands of stars, and we search through the data to look for repeated patterns of dips. So here's an example. This is a randomly selected star. This is a month's worth of data from a satellite called Kepler, which for 3 years stared at 150,000 stars, measuring their brightness every 29 minutes. This is a month's worth of data, so you can see there's a lot of natural variation. The star gets brighter and fainter over time. The camera is operating at the edge of its performance. But I've coloured in here what you can see is a dip caused by a Neptune-sized planet. And so this is how we've got the evidence for the remarkable fact that I started with, for the idea that there are planets around most stars. Of course, we don't just have to worry about single planets, we can find solar systems as well. My favourite is called K2138, planets B, C, D, and F, luckily in that order, which is nice. But this is a remarkable system of at least 5 planets, where the planets are rather special. They're all crammed close to their star. Even F, the outermost planet, is closer to its star than Mercury is to the Sun. So there's 5 planets crammed around the star, but they're in what's called a resonant pattern. So for every 3 times B goes round, C goes round twice. For every 3 orbits C completes, D goes round twice. For every 3 orbits D completes, E goes round twice. And for every 3 orbits E completes, F goes round twice. This is cool because we can use that to make interesting animations. So this is by my friend Matt Russo. What he's done is he's turned the system into a musical instrument. So each planet will cause a chime. The pitch of the chime will depend on the size of the orbit. So we can get this to play. There we go. Do that again. So each planet will have a note based on the size of its orbit. Hopefully you can hear that. And the point is really that sounds musical because there's this resonant pattern. It's actually, you get a perfect fifth between each of the notes. And this resonant pattern tells us, first of all, that these planets formed together. So it tells us something about how these planets formed and evolved. And it also holds out the hope that by studying the interaction of the planets with each other, we can learn a lot more about the system. There's a European satellite called Chaos, which will launch just in the next few weeks, which is going to follow up on this system and watch the transits in more detail and try and work out the masses and perhaps even the structures of some of these planets. But the reason I'm telling you about this system in particular is because it wasn't discovered by professional astronomers. It was found by a bunch of volunteers on a website called Planet Hunters, led by this guy. This is Andrew Gray, who's a mechanic in Darwin in Australia. This is him being interviewed after his discovery. His boss gave him the day off to do interviews as long as he did them at work with a suitable background and in the company uniform. So if you ever need a BMW serviced in Darwin, then you should let me know. Andrew was just so excited by having discovered planets. He was asked on television how he planned to celebrate. He's an amateur astronomer, he has a telescope, and so he said he was going to take his telescope out that night and have a beer with it, which I thought was rather wonderful. But more to the point, we've gone from the first exoplanets, planets around other stars, were found in 1995. The discoverers of those planets just won the Nobel Prize for that discovery. And so in about 20 years, we've gone from Nobel Prize winning science to something you could do with a website. And I think that's illustrative of the speed with which things are changing. I got involved in this because I grew up as an amateur astronomer. Most professional astronomers are sort of refugee mathematicians or physicists who've found their way into the scientific problems that astronomy presents. I come from a different background. I grew up with a small telescope looking at the stars, trying to make a discovery. And in fact, I'd already decided that I wanted to discover a comet in particular, for the very good reason that comets are named after their discoverers. If you discover an asteroid, you have to name it after somebody else. If you find a comet, it's all yours. And Comet Lintott, I still think, has an excellent ring to it. I never found a comet. I did spend ages with a small telescope looking at something called the Orion Nebula. And the Orion Nebula is our nearest stellar nursery to the Sun. So it's a place rather like the nebula in which the Sun would have formed about 5 billion years ago. I love it because when you look at it through a small telescope, you can really see structure in it. You see this green glowing gas which wraps itself around clusters of young, newly formed stars that have just emerged from the mist of the nebula. I was looking at it one evening when I was about 14 and I nudged my telescope and I got this view. The nebula's off to the bottom of the screen here and there's this rather nice little star cluster. This is long enough ago that the best I could do to look up the star cluster was pull out a book. I don't need to explain books to this group, I know, but you get the idea, they don't update. And so I pulled out my star atlas and this cluster wasn't there. And I remember taking a pencil and marking a cross and writing Lintott 1 next to it. And of course, when I got to school the next day, this is actually called NGC 1981. It's not as good a name as Lintott 1, but it was discovered 250 years earlier. So I think that was the point where I realized that I was out of date as to how astronomy happened. It wasn't people with telescopes looking for individual discoveries. And in fact, as I moved on and got my PhD and so on, I realized astronomy had become a science of big data, a survey science. And so instead of using small telescopes, we use things like this. This is the Sloan Digital Sky Survey. It's a 2.5 meter telescope in observatory in New Mexico, where it's clear about 325 nights a year. And for 8 years, this telescope did a remarkable thing. It just stared at the sky, and it allowed the sky to pass over it. It just took pictures of whatever happened to cross its field of view. The only exception to that was on the clearest nights when Sloan went back to the million or so galaxies that it had found, systems like our own Milky Way, and it measured the distance to them. And so with all of that data, that meant that for the first time, we had a decent three-dimensional map of our local universe. So I'm going to show you a bit of that map. I've got about 500,000 galaxies in this animation. We're going to start with the Milky Way, our own system of a few 100 billion stars, and we'll travel outwards into the universe through the Sloan data. And the first thing you notice is that space is pretty big, right? There are gaps between the galaxies. But you get out to maybe about here, and you start to see something else, something remarkable, which is that there is structure. Even on these very large scales, the universe is sort of lumpy. There are places where there are loads of galaxies, and there are places where there are very, very few. If we're writing press releases, we call this the cosmic web. And you can really see it when we get this far out. We'll stop in a minute and rotate the universe for you, and you'll get a proper sense of this sort of honeycomb structure. And this was somewhat unexpected when astronomers found this. And it kick-started a revolution in how we think about galaxies, like the Milky Way. In particular, people started wondering whether where your galaxy sits in this cosmic web might make a difference to the evolution of the galaxy itself. So a galaxy that grows up in the equivalent of a city, a dense cluster, may be different from one that grows up in the middle of a void, an empty region. Our Milky Way, by the way, is sort of suburban. We're sort of neither in a big cluster, nor right out in the middle of nowhere. So that was the problem I was supposed to work on when I moved to Oxford in 2006. Here are two galaxies from Sloan. They exist in different environments. They behave differently, and we wanted to understand exactly how that process worked. Astronomy is a simple science, so we can take these beautiful images and reduce them to really simple measurements. These two galaxies, for example, are different colours. One is blue and one is red. This is a highly sophisticated scientific measurement that tells us about, actually it tells us about star formation. So when you form stars, you form red stars and yellow stars and blue stars. But the blue ones are massive and they burn through their fuel very quickly. So they last for only about, I don't know, a couple of 100 million years or something. And so we know that this blue galaxy on the left has formed stars in the last few 100 million years, whereas the one on the right probably hasn't. But you can also see that these galaxies are different shapes. One's a spiral, one's an elliptical, a big ball of stars. And we've known for about 80 years that the shape of a galaxy tells you about its history. So the shape of the galaxy, if we're being technical, it's the integrated dynamical history, but it's the orbits of the stars that create the shapes that we see. And what that means is that every time a galaxy collides with another galaxy, every time it absorbs material from its surroundings, every time it forms stars and those stars interact, the shape of the galaxy changes. So we realized that what we needed to do was label all of the million galaxies in Sloan with a shape. Now, in the 50s and 60s, people had done this sort of research. Back then, there were a couple of hundred good galaxies available, and so professors would spend their careers labeling galaxies and arguing about the results. By the 80s, new photographic surveys had provided thousands of galaxies, and it was discovered that PhD students could classify galaxies. A few thousand's a bit too many for a professor, so that's fine, you get your student to do that. We had 1 million galaxies. The student's name was Kevin Sherwinski, and we set him the task of working his way through these galaxies. And Kevin, in a couple of weeks, classified 50,000 of these galaxies, splitting them into spirals and ellipticals. And the first result of Kevin's thesis was that that's about as many as a PhD student will stand. That's not quite how he put it, but it's what he meant. The second result was he was better than the neural networks of the time that people had used to attack this problem automatically. It really mattered to have a person do this. And so in sort of desperation, we launched this website, Galaxy Zoo. You'll remember web design from 2007. Yes, this had frames, that sort of thing. And this gave you a randomly selected galaxy, and it asked the simplest question that we thought would be useful. We said, is it an elliptical or a spiral? If it's a spiral, tell us which way the arms are turning. And the idea was that this would be a nice sort of side project. I thought I'd go and talk to people like yourselves, to amateur astronomy groups. Maybe I'd talk to an audience of 50 people, maybe 50 of them would go home and do 50 classifications. And we thought in 5 years we'd work our way through 1 million galaxies. The web doesn't work like that. And instead, on day one, we had 70,000 classifications an hour coming in. And Galaxy Zoo has now received hundreds of millions of classifications of galaxies from well over 1 million people have contributed to this project. The really exciting thing is that taken collectively, those results are good. They were better than the machine learning we had at the time. They're actually better than Kevin, because a crowd will always outperform a single, slightly distractible expert. And so we could sort our galaxies into elliptical to clockwise spirals and anti-clockwise spirals. And just for fun, I wanted to make sure I told you about the clockwise and anti-clockwise spirals. The shape there tells you which way the galaxy is rotating. So clockwise and anti-clockwise is the direction of spin of the galaxy. And we put this question in because we were annoyed by a particle physicist, a guy called Michael Longo, who had looked at a couple of thousand galaxies and said that the universe had more anti-clockwise than clockwise galaxies. And this is a result that makes no sense for two reasons. Firstly, there's a rule in astronomy called the Copernican Principle, which sounds kind of grand, but it's a fundamental assumption, which is that we assume that our bit of the universe isn't special. So any observation you make on large scales shouldn't depend on where you are in the universe. And of course, if I'm looking up at an array of anti-clockwise galaxies, if I fly to the other side of them, I see an array of clockwise galaxies. So that's disturbing. The other thing is that Sloan covered about this much of the sky, and there would have been no time for information to travel from the galaxies over here to over here, not enough time since the Big Bang. And so the only way to arrange this would be a sort of cosmic conspiracy that made sure that all the bits of the universe knew that they were supposed to produce slightly more anti-clockwise galaxies. But 2,000 galaxies isn't a lot. That's like tossing a coin twice, getting two heads, and concluding that all coins always produce heads. And we had 250,000 galaxies. No problem. Easy statistical test. We can tell Longo that he's wrong. Except that we found more anti-clockwise than clockwise galaxies as well, to some insane level of significance. And so we worried about this for a bit. We teased our theoretical colleagues that they didn't understand anything. And then we thought we better check that this was a real result. So without telling anyone, we switched all of the galaxies for their mirror images. So people were now seeing the opposite. So we should then have got more clockwise than anti-clockwise galaxies. But we still got more anti-clockwise galaxies. So it's not the universe that's odd, it's us. Something about how we see these images makes it easier to see an anti-clockwise than a clockwise galaxy. One suggestion, my favorite, is something to do with the rotating figure illusion. I don't know if you know this one. So imagine you're looking down on the cat here. How many people see the cat rotating clockwise? A few people. Good exercise in peer pressure, this as well. How many people see it going anti-clockwise? slightly more. How many people have seen it change? There's a few. First of all, we need to acknowledge that it's weird that we don't agree, right? That's slightly disturbing. If you want it to change, if you do this, it makes no difference at all, but it amuses me. So that's yeah. You see my favourite thing about this slide is I could go and have lunch and come back and you'd all still be sitting here. So the point is that what's happening is that this is a two-dimensional image projected into a 3D world, and your brain has choices to make about how to interpret that. And there are different options, and your brain will randomly choose between them. But over time, there's a bias in any population to one side or the other. So maybe something about how you see spiral galaxies is similar to that in some way. Now, so we ended up doing applied psychology by mistake. Slightly uncomfortable for an astronomer, but we were able to account for this bias, measure it, and the results from Galaxy Zoo went on to be immensely useful and interesting. I don't have time to tell you about all of them. I thought I'd just pick out one piece of work which I thought would be interesting. At the center, so that was a map of our galaxy. It's got a bar at the center, which is good news, a couple of spiral arms. But right in the middle of our galaxy, we have a remarkable thing. These are stars near the center of our galaxy. And this is data taken over about the course of a decade using the Keck telescopes on Mauna Kea in Hawaii. And what you can see is that we're able to get sufficient resolution that we can see how these stars move. They are, in fact, in orbit around something at the center of our galaxy. And because we know how massive the stars are, we vaguely understand stars, we can work out that the thing at the center that they're orbiting must weigh a few million times the mass of the sun, and that mass must be crammed into a volume of space that would fit within the orbit of Neptune. And our physics says that that must be a black hole. So this is the best evidence we have for the presence of a black hole at the center of our galaxy. Now, our galaxy, this black hole, is a perfectly friendly beast. It's reasonably quiescent. But if you overfeed a black hole, then things can happen. This is the nearby galaxy M87. It's a bigger galaxy. It's got a much larger black hole. Material is falling down onto it right now. And you can see there's a jet of material that's had a very lucky escape. It's ejected just before it falls into the black hole because of some complex physics that goes on right at the center. And in fact, there's a general rule that we've discovered about galaxies. It's very simple. The more massive the galaxy, the more massive the black hole at its center. So the bigger the galaxy, the bigger the black hole. And this is kind of interesting. Physicists like things that are aligned like that. That feels like we're getting some insight. But actually, it's also confusing because our galaxy weighs a few 100 billion times the mass of the sun. And the black hole at the center, although we call it a supermassive black hole, it only weighs about 3 million times. So million versus hundreds of billion. So the black hole should be completely insignificant. And yet somehow, whenever we look at a galaxy, we see how massive the galaxy is, the black hole is roughly the same mass. And so this is a problem that needs explaining. And there's a natural explanation that people have reached for, which is through colliding galaxies. So this is a computer simulation of the future of our galaxy. Now, I said we live in the suburbs. We actually live in a little local group of galaxies. There's us, there's the Andromeda galaxy, and there's another spiral called Triangulum. The clock's ticking in the bottom right of this image, and in a few billion years' time, the Milky Way and Andromeda are going to merge with each other. So there'll be a dramatic collision between the two galaxies. Now, it won't be as dramatic as it sounds. There's enough space between the stars that no two stars collide in a collision like this. But the two galaxies, in about 4, 5, 6 billion years' time, will collide to form a single galaxy, which I'm afraid to say some of my colleagues like to call Milkdromeda, because astronomers shouldn't name anything. I'm realising I don't have any power here, and this is about to go to sleep, so that's going to be interesting. Could somebody else come and fiddle with the power? Thanks. So there's a natural explanation here for what's going on. If galaxies grow mostly by merging with each other, and if their black holes combine after a merger, then you can grow the two in step. Your galaxy gets bigger, so when the Milky Way collides with Andromeda, it will double in mass. if their black holes collide, that will be a doubling in mass as well, and you can explain this very naturally. But we needed to test this idea, and we used Galaxy Zoo. In fact, my colleagues Brooke Simmons, now at Lancaster, and Becky Smethurst, now at Christchurch in Oxford and also a YouTube star, used a set of galaxies derived from Galaxy Zoo to test this. They took a bunch of spiral galaxies that, because of their shapes, we could tell never had a merger. And so these are guaranteed merger-free galaxies, and we could measure their black hole mass. And we expected them to have much smaller black holes than we would otherwise expect. But it turns out they have the same size black hole as a normal galaxy. And so mergers are not the answer to this problem. We've done that very scientifically joyful thing of ruling out the only obvious hypothesis, which is great fun. But there's a broader point here. Brooke and Becky and myself ended up using a sample, they're all on screen, of 120 galaxies. But I started this talk by arguing that astronomy is about big data. Right? We started with 1 million galaxies. We end up studying 120. And that pattern keeps happening. You start with these large data sets, but actually what we're mostly trying to do is find the right things to look at within the data set to simplify a problem and gain insight that way. Which brings me on to penguins. It turned out that astronomers are not the only people who struggle with getting too much data. This is an image from a camera network run by my friend Tom Hart, who used to go to the Antarctic to count penguins. He describes himself as a penguinologist, is thus on BuzzFeed's list of the top 10 job titles ever and that sort of thing. Tom used to go once a year to each penguin colony and count them. He's interested in whether climate change is affecting them, or whether fishing in the Southern Ocean is a problem, or whether the increased tourism in Antarctica is causing a problem. He used to go once a year and count and compare how they were doing. But obviously, if it's raining one year and not the other, or if the spring had been sunny and the penguins had nested earlier, or if a tourist ship had been an hour before Tom turned up, the data's pretty sketchy. And so Tom realized he could take cheap off-the-shelf cameras and a car battery, set up a network of cameras that could take pictures like this every hour, and he could monitor the penguins over the course of a year. So this is a typical image from... It actually looks like the penguin's taking action against the camera, but I don't think that's what's going on. A typical image, and Tom has simple questions. He comes back to Oxford with 8 million of these images a year. He needs to know how many penguins are in this image. So audience participation time, how many penguins are in the image? 3? There's usually somebody who says 2.4, but I like 3. 3 is a good answer. We'll do one more. Just shout out when you've... So I heard somebody said lots, which is good. This is an excellent demonstration of the advantage of having people rather than a neural network do this, right? Because you're able to think outside the training and reject the premise of the question. Lots is a good answer. So we used the same software that built Galaxy Zoo to build Penguin Watch. And so now we have people all over the world counting penguins for us. Every time I show this slide, I'm reminded the original name of this project was Penguin Hunters, which I think you can see in the design. But apparently that wasn't acceptable. And in fact, I have to mention as I'm here, a Google Global Impact Award let us build not just individual projects, but a tool for building projects. So researchers can now log on and very quickly put a project together to ask the Zooniverse community to engage with their data. And we built all sorts of projects with it, including this one. This is the Planetary Response Network, which is a partnership with a NGO called Rescue Global, who do quick response to things like the hurricanes in the Caribbean the other year, where we do rapid assessment from satellites of which roads are passable, which buildings are standing, and so on, using the power of volunteers. I think at this point, hopefully I've convinced you that this sort of scientific crowdsourcing is fun, that there's an audience for it, and it produces useful and interesting results, whether it's for penguins or galaxies. I want to spend the last 10 minutes, really, as I spend the last half of the book, making 2 separate arguments. The first one I call the Gorilla problem. So this is these are images from another camera trap project. This is Snapshot Serengeti. These are motion-sensitive cameras distributed across the Serengeti National Park, which take pictures every time an animal comes past. So we've got a giraffe, a lion, porcupine, stripy horse. I don't know, I'm an astronomer. And some of these images can be really beautiful. And some of them, you'll have realized, present a pretty easy machine learning task, especially these days. So, for example, in the top left, that couldn't really be anything else other than a giraffe. We now have a set of, I think, 350,000 images of giraffes from the camera network. It's trivial to train a straightforward CNN or something like that to recognize giraffes. In fact, we've built the world's best open source giraffe detector. So if you're ever worried and need to check your environment for giraffes, you can do that. That's one of the things the Zooniverse has produced. But one of the animals that appears in the network occasionally is this thing. This is a zorilla. It's a small skunk-like creature. They appear in 1 in every 3.4 million images that the network takes. And so building a training set of zorillas is really difficult, or at least very time-consuming. And in astronomy, we have a lot of space zorillas. This is not a real picture. This is a montage. But despite, I think we're in I'd like to clarify these things. What I mean is that even though we're dealing with very large data sets, most of the time there's value in the very unusual in our data set. So you may have heard of things like gravitational lenses, where the light of a distant galaxy is bent by a nearby galaxy. That allows you to find out all sorts of things about both lens and the galaxy that's lensing. But we only have a few hundred of those. And so machine learning approaches are possible, but they're difficult because we're stymied by the lack of training data. And one of the things that we found with Zooniverse is that we should also be aware of the very unexpected. This green blob, imagine I trained an algorithm to classify galaxies. If I showed it this picture, it might well get the fact that this galaxy at the top is a spiral galaxy, but the rest of you are wondering why there's an evil version of Kermit the Frog hanging in space underneath it. And this thing was first spotted by a Dutch school teacher called Hannie van Arkel. Hannie called it the Voorwerp, which we thought was a technical word. I think it means thingy or object in Dutch. But it's now known as Hannies Voorwerp in the literature. And it's an immense galaxy-size echo reflecting light that comes from activity around the galaxy a few tens of thousands of years ago. It's become an object of immense interest. We didn't know to look for these things, and yet because Hannie found it, because she was an advocate for it, she did the simple scientific thing of asking what this weird thing was. Not only do we have that object, but a bunch of other volunteers went and found lots of these glowing gas clouds that you can see in green here, and pointed out that we should really pay attention to them. We've even had volunteers carry out their own research studies. This is a set of light curves, so this is brightness against time for a particular star, one of the 150,000 stars that the Kepler satellite was observing. You can see they have this sort of shark fin dip. So this is the star, it dips rapidly and then it recovers rather slowly. These were discovered by a volunteer called Tom Jacobs, who read an old paper, realized that this is the kind of thing that you'd expect if you have not a planet going in front of the star, but a comet. And then the paper explains that he therefore looked at the data from 200,000 stars and found the one example where this is observed to happen. And then he emailed some professional astronomers and handed them the discovery, and they wrote a paper together. So looking for the unexpected is important. And I think as data sets get larger, that means that we keep open a place for this sort of scientific crowdsourcing. I think we're going to have to do that because we're building telescopes like this one. This is a mountaintop in Chile with a building that will be an observatory on it. This is the home of what's going to be called the Large Synoptic Survey Telescope, LSST, because astronomers shouldn't name anything. LSST is a remarkable thing. It's as big as the biggest telescopes in the world today, but it's a survey telescope. It's going to scan the whole sky every 3 nights. We think we'll get about 30 terabytes of image data a night. And if that's not enough, LSST will broadcast an alert every time it thinks that something has changed in the sky. And so if you subscribe to those alerts with your phone, we think you're going to wake up to about 15 million alerts a night. And that will include new near-Earth asteroids, distant Kuiper belt objects out near Pluto, the flickering of stars, which are almost all variable when you look at them with a large enough telescope. We'll even see the centers of nearby galaxies will flicker as material falls down onto their black holes at their center. There'll be catastrophic explosions, supernovae and gamma ray bursts and so on, but in there will be things that we haven't even thought to look at. And what our challenge at the minute as data scientists doing astronomy is working out how to find those things. And we think the answer might be combining the kind of citizen science I've been talking about with modern machine learning. That's not a particularly new idea. We've been thinking about it for a long while. In fact, back in 2015, we ran a Kaggle competition using the Galaxy Zoo data. It was a won by this guy. This is his paper by Sander Dieleman, who's now here. Hey, how are you? Credit, thank you. Who taught astronomers about CNNs, basically, through winning this competition. Actually, the thing I got from this competition was that the astronomers who entered did really poorly. And we realized we needed to collaborate with experts in computer science and so on. But we've also been thinking about this in sort of terms of looking for supernovae. So we've run Zooniverse projects looking for supernovae, for exploding stars, for changes in the sky. We've ran one using data from a telescope in Hawaii called Pan-STARRS. And for this project, we had volunteers classify every possible supernova. But we also ran a trained CNN, convolutional neural network, trained on expert classifications. And I want to show one graph, I think, in this talk, mainly because I like graphs. So on the bottom here, you've got the score that the machine gave this. So if something's on the far left here, the machine was sure that it was not a supernova. If it was on the right, the machine thought it was definitely a supernova. And then the human score, the score from volunteers, is here on the bottom left to the top right. So at the bottom, definitely not a supernova. At the top, definitely a supernova. And then the colors on each point is a possible supernova, and the colors are the expert judgments. So green are definitely not supernovae. Yellow and red are possible supernovae that we'd want to go and follow up. Blue are asteroids, which for this purpose are the same as supernovae. You discover they're asteroids when they move. So that's the secondary thing. And so what the task here is to divide green from the other colors. And you can see, I think, that the way to do that is to put a diagonal line on this graph. So there's no cut just on the machine score or on the human score that outperforms the combination of two. And we've discovered this is a general point, a general principle in what we're doing, that for the kind of messy data sets with poor training that we have available, the combination of human and machine working together produces better results than either human or machine alone. So we have this beautiful future in which humans and robots can coexist. Now, we could be much more sophisticated than that. My student, Mike Walmsley, has built a neural network that predicts, not a classification, it predicts the vote fraction, it predicts what a crowd of humans would do when presented with an image of a galaxy. And it has a probabilistic understanding of how confident it is about that classification. So what we can do is we can take, first of all, we can take the galaxies that the machine is least confident about and prioritize those being seen by the volunteers, so that people are doing the work that we exactly need them to do, and the machines are doing the other stuff. And so far that's working well. We've discovered that, for example, I can actually show you. So this is a set of recent Galaxy Zoo galaxies. On the left, these are the galaxies where the machine is most confident it's got its classification right. And on the right, those where the machine is least confident. And you could sort of, I never quite know what to say about this slide. I think it's slightly intuitive. On the left, they're mostly simple systems, often spirals, relatively nearby. On the right, you've got some unusual objects. There's a nice ring in the middle of the bottom row there, some artifacts, the red and the yellow on the right-hand side there are problems with the camera or with the data processing. But I'm not sure you necessarily guess which of these the machine would get right. But we're able to actively and programmatically pass what we need to do to the volunteers. And in fact, we could get better than that. We can get the volunteers to look at the things that the machine thinks will most likely improve its classifications. And so we have this loop between human and machine, with the volunteers picking up on the ever more unusual and interesting things. And that's the combination of technologies that we think we'll need to deal with the data set that's coming. And so in the end of the book, I end up arguing about the three possible futures. There's definitely a future in which machine learning wins, but I think we miss out on our gorillas. There's a future in which we decide not to go that way, and we sort of trick people into classifying because we think it's good for them, because it's good science communication, and don't tell them that that off-the-shelf technologies, the kind of things that you here are developing, could do most of the work. But there's this middle path where people get to do the interesting stuff, and we get better results out at the end. Now, I've talked about this all as if it's a new set of ideas, as if we've gone boldly into new territory and thinking to involve a large crowd of people in scientific research, but it's actually an old idea. So I want to finish with this guy. This is Arglander. He was a Prussian scientist in the 19th century who invented the study of variable stars. He was the first to realize that you could systematically study how stars change in brightness. So that's the branch of science that really led all the way to the discovery of planets that I started with. He decided that he could not make all of his observations himself, and so he put out a call to everyone in the world who had been observing stars. And he said that if they helped him, they would perhaps in a few years be able to discover laws in the apparent irregularities in the brightness of the stars, and in a short time accomplish more than in all the 60 years that have passed since the discovery of this phenomenon. I've got one request, he said, which is this: that the observations be made known each year, because observations buried in a desk are no observations. Should they be entrusted to me for reduction or even publication, I will undertake it with joy and thanks, and answer all questions with care and with the greatest of pleasure. It's a wonderful example of how one collaborates with an enormous group of people. I'd be very happy to answer any questions with care and the greatest of pleasure. Thank you very much.
Thank you very much. So if you have questions, I'll come around with the microphone.
Have you thought about getting more people to help with this classification by using these in captures, things like that?
That would be amazing, especially now we've got we have in many cases a machine hypothesis. So the task is this right or not? So yeah, we talked to Louis Van Aan about capture years ago, just before I think he ended up working with Google, and then we never followed up. But it's an amazingly good idea. So thank you for asking. I love the idea that people would be accidentally doing science as well. Like, we've talked about replacing our homepage with, because at the minute you have to come and choose a project to work on and so on. We've talked about having the first thing that happens, we show you an image and we say how many penguins are there, so that you can start the conversation by saying, actually you just did some science. Maybe it could be a fun Google Doodle or something as well. Just surprising. I should have said really, I expected to be talking to amateur astronomers about doing this. Actually, we find most of our volunteers don't have a background in science, don't have a prior hobby interest in science. They sort of stumble into it and then become people who can do science and are interested in it. And that's from a science communication point of view, that's the really exciting thing.
Hi, what are the new challenges that you've seen for the astronomer, and in particular, let's say the SpaceX launches and all the satellites?
We're busy arguing about it right now. So, for those who don't know the story, the suggested number of large constellations of satellites are going to have a significant impact on the kind of work that I've been talking about, particularly with LSST actually, because the reason LSST is so powerful, it's been built to have a very wide field of view so that we can survey the whole sky. So that means you're very sensitive to things like large fleets of satellites crossing over. And the problem's not as simple as knowing where the satellites are, because you see the satellites, but you also see ghost images of them because of the reflections in the optics and because they're moving and so on. So at the minute, friends of mine are in the middle of an assessment to see whether SpaceX has affected our science, and the answer will be yes, and the question is how much. I think there's a cost benefit here. Obviously, if you can provide, I don't know, free internet and YouTube for everybody forever, versus make it slightly more difficult for astronomers, we maybe make that trade-off. But no one's doing that sort of cost trade-off. I don't think people have realised as well. I'm an astronomer because I grew up looking at the stars. I think everyone should have the cultural experience of going and looking at an unspot night sky. And if you do that after sunset now, about half the time you see the SpaceX constellation of satellites fly over. And even when they're in operational mode, they're visible to the naked eye. So you're going to see a sky that we've affected. And maybe that's okay, but we don't have a mechanism for having that conversation. In general, though, you asked about general priorities. I think my main worry is how we keep open a space to be surprised. Whenever we've opened new telescopes, new ways of looking, we've got most of our science out of things we didn't even expect to be looking at. I went and looked the other day at the original proposal for the Hubble Space Telescope, and then the 10 science priorities when it launched. And if you made a list of the 10 greatest achievements of Hubble, I think 2 of them match out of the 10. And so I think as we become more a data-driven science, we need to find, as I've said, need to find ways to make sure we can be surprised.
So you say on Galaxy Zoo, the examples that are most likely to be shown to volunteers are the ones the machine will struggle to classify. How do you factor for example, the galaxy being quite simple for the machine to classify, but also has something completely unexpected like the Voorwerp in the image as well that would otherwise be missed if a volunteer didn't follow that?
That's a really good question. So at the minute we're doing the crude thing of all galaxies are seen by some people, in the hope that we'll keep up this rate of the unexpected, because the Voorwerp wasn't classified as a galaxy, it's just in the background. There are other good examples. There's a set of galaxies called the Galaxy Zoo Ps, which are small, round and green, so the volunteers called them Ps. But they're in the background of the images. They were investigated by a bunch of volunteers who called themselves the Peas Corps. And it took me ages to realise that was a joke. And yeah, they turn out to be the most efficient factories of stars in the local universe. So at the minute, we're sort of backstopping by having 3 or 4 people look at every image in the hope that we'll still get the unusual. Obviously, one could build optimized machine learning attempts to find the unusual stuff. Finding the interesting unusual stuff is really hard as an ML problem. But we're looking at, for example, ways of doing clustering or so on. So you might end up with you could easily cluster the weird stuff together and then have people go through that. So we may end up with a targeted search for the weird rather than a classification with accidental discovery of the unusual. But that's an experimental question right now. As to whether it's better to separate those approaches or work on them together. We've also got to worry, of course, about what people want to do. So far, the galaxies that our galaxy classifying machine wants people to look at are appealing to people. But you can equally imagine that might not be the case for all problems, right? So if, for example, we haven't done this yet, but on Snapshot Serengeti, you can imagine the machine getting all the nice, beautiful images right, and all the fuzzy things of a distant shape in the dusk, which may or may not be a sort of antelope being presented to the public. So then I think you have to think hard about what you're doing and how to balance these things.
Thanks for the talk. That was really interesting when you said you discovered the bias of people to classify anti-clockwise more than clockwise. Did you discover anything similar, or what would you expect? Where would you look for similar bias?
I think that's the most counterintuitive one, or the most surprising one. In project, the other thing that swings to mind is we've had projects where people have looked where we're looking for unusual but not that rare things. So we did a project using Hubble Space Telescope data, which made an amazing map of the Andromeda galaxy. A project called PHAT, P-H-A-T, because astronomers shouldn't name things. But you look at these star fields, and the task is to look for clusters of stars. And we found there's what the research team called a distraction bias. So once you find one cluster, you stop looking. And so we had to very carefully take that into account when we were looking at the density of clusters. And so we spend a lot of our time making sure we measure these things. And one thing that I think is interesting is that these biases would be apparent, I think, whatever classification method you used, but we get to talk to our black box because it's got people in it, and we can ask them why they didn't see things. And people don't obviously self-report their biases, but that makes it kind of easier to unpick what's going on. The biggest bias, though, is that people don't think they can do this. People get very scared by the fact that this is real science, right? The idea that I can give you a graph and ask you whether there's evidence for a planet in it. If you think of it as a silly website game, then fine. But if I tell you that NASA scientists are relying on you to discover planets, then it begins to be a bit scary, and people's results get worse the more they believe that they're really contributing. And so we've spent a lot of time working out how to reinforce the message that there are other people around, that it's not just your classification. We found that was particularly problematic when we did projects with Cancer Research UK, where the strapline on the project was, you can help us cure cancer. And it turns out that's not inspiring, that's terrifying, right? If what you do in your lunch break genuinely could make a difference to whether we cure cancer or not, then maybe that's not quite such a relaxing activity. And so a lot of the biases are around how we think about ourselves in relation to science, and sort of helping people understand what we're asked to do, and that everyone could do this sort of thing. It turns out to be really important. Thanks for the question.
Any other questions? I have one for you, actually. So you mentioned earlier that you've been getting, you had a grant from Google that helped support you. Are there other things that you need for the Zooniverse project right now as far as resources, or is it literally just people to partake in?
Well, we have a large project to keep going, so we have a standing army problem, so we're entirely grant funded. But we run this service where researchers can build and run these projects at no cost to the research groups. And we do that really specifically because when I was a postdoc setting up Galaxy Zoo, if I'd had to apply for money to do it, I'd never have done it. The people who are on the front line of dealing with the data aren't the people with access to large grants or resources or so on. So we try and keep that out ourselves. One of the most interesting partnerships, we've been working a bit with your colleagues in Boston to look at how we can use Google ML tools that are available on the web and make it easy for Zooniverse researchers to do the kind of sophisticated combinations of machine learning and human classification. So that's been a great partnership, and we've really enjoyed doing that. But yes, if anyone wants to write a large check, I will happily take it.
All right, well, thank you
very
once more.